Hi everyone, and welcome back to our last afternoon of the Open Web Forum, curated by Fabric Ventures. We're here for a panel that I'm excited to learn more about, a post-quantum world, what will be crypto's role then? Moderated by Michael Harte. Michael is a research fellow at MIT. Quantum computing has the potential to break existing cryptographic algorithms. What can we do to prepare for an impending post-quantum world? Handing over to Michael to tell us more.
Thank you very much. And it's exciting because I have two of the very best for you today. I have Eli and JP. Eli is the co-founder and president of StarkWare in Israel, and JP is the co-founder and chief security officer of Taurus in Switzerland. I'm going to ask both of them to kick off quickly with a 2-minute primer each. And I'll ask JP to go first, and perhaps JP, you could update the room on your latest book.
Well, thank you, Mike, and thank you for having me in this panel. Very happy to be here with you and Eli. As a very quick introduction, I've been interested in the topic of quantum computing and post-quantum crypto for approximately 10 years now. So my field of expertise is cryptography, applied cryptography, and now blockchain security. And I've also designed some post-quantum algorithms. And I've done a lot of outreach to explain and to try to simplify the concept of quantum computing. And yeah, very happy to be here today to talk about this with you.
Fabulous. And do you want to give us a sneak peek at the book and tell us what you are telling the community about the current state? And we'll get to the future state, but a current state update from you would be fabulous.
Yeah, thanks, Mike, for mentioning it. So the idea of the book is to explain all the cryptographic terms used today in a very simple terms. For example, you will find Starks and Snarks and zero knowledge and blockchain and quantum computing mentioned in the book. And the idea is to make it very easy for everyone to follow.
Wonderful. Now over to Eli. Eli, thanks for dialing in, and give us a quick introduction of your work at StarkWare.
Yeah, so thank you for having me on this very interesting session. So I'm co-founder and president at StarkWare. StarkWare is an Israeli startup with about 45 employees, and we're developing proof systems for privacy, zero knowledge proof systems, and for scalability on blockchains. These systems are called ZK Starks. They happen to be post-quantum secure, among many other good attributes that they have. So I'll tell you a little bit about them. And I'm not as big an expert on post-quantum cryptography. My background is more in math and computational complexity. I've done about 20 years of postdoctoral research, and then I was a professor of computer science at Technion, and I researched proof systems, which, from theory to practice, which led me to being fortunate to be a co-founder both of the Zcash cryptocurrency, which uses ZK Snarks, and also of StarkWare, which uses ZK Stark. So I hope to share a little bit about those things in the context of post-quantum computing.
Okay, so let's start off with some access for a wide audience and an intrigued audience around the current primitives of cryptography and the current state. Let's sort of demystify and update the organizations that are represented in the room around where different primitives in cryptography are being used in the Web3 stack today. You know, you've got proof of work, you've got zero knowledge, you've got Merkle state, you've got transition or transaction execution, you've got key exchange. A lot of this is around, as you say, the complexity of some of the new communications, some of the new protocols, and a lot of it is around scaling problems. Each of you perhaps start with Eli talking about some of these scale problems in just current state cryptographic problems.
Yeah, so let me give a very brief lay of the land of crypto primitives as they appear inside the world of blockchains. So within cryptography, first of all, you have primitives. These are the very basic building blocks, and they serve different purposes and have a lot of different constructions. So some of the major, and then they're like huge families of them and interactions between them, and I won't mention all of them. I'll just mention some of the more relevant ones within the context of blockchains. So first of all, within cryptographic primitives, you're going to break it up into symmetric and asymmetric cryptography. Symmetric cryptography are things that usually involve the same sort of key for both the sender and receiver if it's an encryption system, and they are much older in construction, and they are simpler to design and work with, and there's a larger design space for them. And so within the symmetric cryptography branch, you have things like hashes. So hashes, I think you should think of them as these fingerprints, cryptographic fingerprints. It's a way for you to get, take a big file or a big piece of information and get some fingerprint from it. It's in the end, it's a sequence of bits because everything is digital in our world that we're discussing today. But it behaves like a fingerprint. So it's something very unique. It's something very succinct. Something where you can tie uniquely to a single entity or a data file or something like that. So that's a hash, and hashes are really, really important in a lot of things, from protecting against viruses and attacks. And in the context of blockchains, they're used all over the place for instance, for mining. Okay, and then you have things like asymmetric cryptography, that things like digital signatures and things like that, where basically there are two different keys. One is used for generating messages and the other for authenticating them. And these are two different keys, and usually one is kept private and the other is made public. And these are used, for instance, for signing on payments and things like that, and for basically my identity is owned by myself knowing some key within a cryptographic context. So the way I own Bitcoins is by knowing a key in an asymmetric cryptography system. So we have symmetric crypto and we have asymmetric crypto. And then within the world of symmetric cryptography, pretty much almost all of it is pretty safe from quantum computers. And then and this relates, building Merkle trees and computing hashes and proof of work and things like that. Whereas within the asymmetric world, a lot of the most popular and most efficient constructions, for reasons that we'll discuss maybe later, maybe Jean-Philippe is going to discuss, those are far more breakable. So I think I'll limit my answer to that and hand it over.
Yeah, so JP, from your perspective, where do you see some of these primitives, and where are you seeing some of the current scale problems, and specifically around blockchain and smart contracts or other assets, other new classes of assets?
Yeah, well, thank you. Eli gave introduction by breaking down it into symmetric crypto and public key crypto, and he mentioned hash functions. So hash functions, they're like the backbone of blockchain applications. If you had no hash functions, you would have no cryptography at all, because a lot of things can be built from hash functions. And the good news is that hash functions, they are fundamentally immune to quantum algorithms. Whereas, as Eli mentioned, some public key algorithms, and in particular signature algorithms, are vulnerable to some quantum algorithms. And this is important because most of all the crypto we use today, if you connect to a website, if you connect to e-banking, if you send a blockchain transaction, so in 99% of the cases, you will rely on some form of public key crypto that is vulnerable to quantum algorithms. And in the case specifically of Ethereum, of Bitcoin, is the specific case of what we call elliptic curve cryptography, and more specifically the ECDSA signature algorithm. So I would like to stress that I mentioned quantum algorithms, which are a different way of computing that would rely on the quantum computers. And this is why we are here today. That's why we have this panel, because quantum algorithms, they could solve some crypto problems that we cannot solve with the classical computers we have.
And how are these things actually being attacked? Where are we seeing this new surface area, and how do the attacks get perpetrated? And can you give the audience more insight into perhaps a couple of cases or a couple of examples?
Well, the good news today is that we don't use quantum computers to attack things, because quantum computers don't exist, at least in a size that would be useful. So when you mentioned are they attacked, well, hopefully they're not attacked too much. But the biggest problem in cryptography, I mean, for all the audience who has worked with cryptographic engineering, it's not designing ciphers, it's not even zero-knowledge proofs. The biggest problem is key management, managing your keys, having backups and so on. So what we see in practice oftentimes is crypto being not compromised directly, but just walked around, either because someone has leaked the key, or just the crypto has been completely bypassed. So the cryptography is generally not directly attacked, because mathematically it's very stronger.
And where are you seeing specific cases in any of the cryptocurrency domains, any of the blockchain environments, or W3 today, whether it's quantum or not?
I don't know, maybe Eli has
Okay, I want to say something about attacks and the way that they are carried out in general. So I, of course, agree with Jean-Philippe that often it's the more prosaic things that prevail, and these are the attacks that happen. These are the day-to-day attacks. But in terms of core cryptanalytic new techniques and core mathematical new attacks, the way what really happens is that when you construct a primitive, and this pertains more to the world of asymmetric public key cryptography, you're going to have to use some mathematical structure. Usually it comes from number theory, from the theory of prime numbers, or some more elaborate constructs on top of that, like lattices or elliptic curves and the groups that are facilitated by them. So all of these things have structure, and as a cryptographer designing new primitives, you're basically using that structure to do all kinds of very funky stuff like public key crypto systems. As an attacker, you're going to rely on the same structure that these mathematical objects have to find ways to basically circumvent the need to go and try and check each possible key, right? You're going to use some inherent structure to speed things up. And one very famous attack is basically, if you can factor numbers more quickly, then you can break a lot of these crypto systems, especially in the many of the prevailing asymmetric crypto world. So, and factoring has it's a very basic mathematical problem that people have been fascinated with since Eratosthenes, right, and his sieve. And there are many advances that basically by now have made it much faster to find the factoring of a number. And essentially, when people talk about the threat of quantum computers, one of the biggest things that they can achieve is factor numbers really quickly, again, using the kind of structure that some of these problems have. And this, going to the world of blockchain, has huge implications, because basically, if ever a large-scale quantum computer were to exist, a lot of the keys that protect your currencies and whatnot, your funds, are now can be easily retrieved, and everything would sort of break unless you replace it with other primitives that are post-quantum secure.
And what are some of those that we're starting to see being worked upon? What sort of solutions do we see? We talked about some pretty crude and cumbersome things. There's some Lamport signatures or starts that you refer to, or new algebraic references or lattices. What are you seeing emerging? And yeah, go ahead.
Yeah, maybe I can take this one. I think, like Eli mentioned, quantum algorithms, they have the capability to solve certain problems fundamentally faster. So instead of exponential time, so to speak, it would be polynomial or sub-exponential time. However, what's important to know for the audience is that quantum computers, they would not magically solve any problem, and specifically, they will not be able to solve the problems that we call NP-complete problems, which means problem where the solution is easy to verify as a correct solution, as a valid solution, but it's very hard to find. So I'm simplifying a lot. So what it means is that we can rely on this class of problem, called NP-complete problems, to build cryptography that would be resilient to quantum algorithms. And secondly, we also mentioned hash functions, and we mentioned that hash functions would not be broken by quantum algorithms. We know it relatively well. And another class of post-quantum, so post-quantum is algorithms that would not be broken by quantum algorithms. So one way to get post-quantum crypto would be to rely on hash functions. But we just told you that hash functions are symmetric, not asymmetric. And here the fantastic result is that you can create digital signatures by only using hash functions with a mathematical proof that as long as your hash function is safe, then your digital signature scheme will be safe as well. But it only works for signatures we don't know, and we have good reason to believe that you cannot create an encryption algorithm based on hash functions only. So yeah, the idea is to rely on problems that we know are very immune to quantum algorithms and to try to use them to build what we need. So specifically digital signatures, but also encryption or key agreement protocols, such as alternatives to Diffie-Hellman.
Yeah, if I can add to this, excellent answer. So you can think of, again, sort of the work, the cryptographer and cryptanalyst are sort of usually like maybe Mr. Dr. Jekyll and Mr. Hyde, right? They're like two facets of the same creature. And what you're doing is there's of course math underlying everything, and math is the study of structure. And then you want to find sort of the right balance between having enough structure to do things that will allow you, the good players, let's say, to encrypt or to sign or to prove integrity or authenticity, whereas the bad players or the attackers to not have enough structure to do something. And if I'm just going to mention like 3 different kinds of points along the spectrum of structure to disorder. So things like hash functions and symmetric encryption, they lie at the chaotic extreme of these are objects that typically they are designed to have almost no structure. So think of these functions as basically taking bits as their input and really just messing them up in the worst possible way that even the designers don't really understand what's going on, and that's the purpose. So these are like have very little structure. And because they have very little structure, they are often extremely efficient to implement in hardware. They're very fast, they're very resilient. A lot of them have very few attacks, and they don't have enough structure for you to, let's say, take a quantum computer and do anything significant to them, okay? Then you have, I want to mention 2 things that are sort of 2 varieties. So one of them is number theoretic stuff. Based on the structure of numbers and all kinds of their beautiful properties and prime factors and whatnot. And this is at the extreme of structure. I mean, there are things with even more structure, but then they can't be used for cryptography. And these are beautiful things in which you can build very efficient key exchanges, and you can do 3-way key exchanges using elliptic curves, and you can do a lot of amazing and beautiful stuff. But because they have so much structure, this structure leads to certain attacks, the generalized number field sieve, which factors things faster, and of course shows quantum factoring algorithm and things like that. Now, a third option sort of in between is using what's called the learning with errors paradigm, which is this other thing that has a little bit of structure, but maybe it's just the right amount for dealing with cryptography. It is basically some version of Gaussian elimination, but with noise. And Gaussian elimination is extremely efficient, but once you have put the right kind and amount of noise on it, becomes very unstructured, and it is like this very nice point in the middle between structure and unstructured. So things based on learning with errors are right now prime candidates for using and looking for post-quantum constructions. And the other one that Jean-Philippe was referring to, and this is what StarkWare actually does and deploys, is to take the weakest or the least structured of these objects, which are called hashes or symmetric cryptography, and add them as the only ingredient that is cryptographically necessary to some very powerful algebraic and proven mathematical protocols that come from the world of complexity. These are interactive proofs, zero-knowledge proofs, probabilistically checkable proofs, Starks, and interactive oracle proofs. There's a large number of critters there that have very strong mathematical guarantees and require very minimal cryptography. And this is the kind of mixture that gives you some cryptographic primitives. For instance, you can get digital signatures that are post-quantum secure using these things. So I mentioned, like, there's hashes and no structure. There's number 3 of theory with too much structure. There's the Goldilocks learning with errors that seems to be just right for building some stuff. And you can also take the least structured, add it to some very strong mathematical structures, and get some of your primitives back.
And I like how you describe it, because it's also, I like describing symmetric crypto as something completely chaotic with no structure. And if you have some kind of structure, then it's called an attack, it's called a distinguisher. And it's the way it is secure is also the very reason why we don't have formal guarantees, why we don't have proofs. Because the very reason why it's secure, according to our security definition, is what prevents us to leverage the structure to do reduction proof, or to show that solving a certain problem is at least as hard as a well-known problem. And maybe also to elaborate on what Eli was saying, so you mentioned the LWE learning with errors problem. And just to tell you that it's not just research stuff, it's really concrete. So there's a standardization effort ongoing by the NIST, US federal agency. I think they're going to choose the final candidate, the final standards, probably later this year. And yeah, and in my understanding, some of the best placed candidates and most of the finalist candidates rely on this problem, on the LWE problem, which is in itself beautiful, because we go from something very simple, solving a linear system of equation, and we add noise, and we can demonstrate that on average, if you take an average instance of this problem, then it's on average at least as hard, is equivalently as hard as to solve as the hardest case, as the worst case of another type of problem related to mathematical lattices. So the math is beautiful, and interestingly, the randomness is trying to break the structure to make it hard as a computational problem.
Why don't you spend a little more time on lattices and open up that very arcane and mysterious world to a broad audience? Because, as you say, there is some real beauty in there.
Well, it would get quite technical, so we don't want to go too far, but maybe what important points. So I think that the best way to summarize it is, without giving too much detail, is to say that you have a relatively simple problem, mathematical problem, solving a linear system of equations, and you add some noise with a given normal distribution, so you know the distribution of the noise, and what you see is the result of the equations. And your goal is not only to solve the equations, so find the hidden variables, but also to distinguish this from random. And what researchers have been able to demonstrate is that the result of the equations with this added noise is hard to distinguish from random. And if you could distinguish it from uniformly distributed randomness, then you could solve a computational problem related to mathematical lattices. So I'm not giving the proof in detail. There's a very good survey online. You can look up the work by Oded Regev. It has a very nice survey about this. And maybe just to finish on this point, what is still keeping researchers busy, and there's a lot of controversy, So if you take the case of symmetric crypto, you take the AES encryption scheme, you have a key of 128 bits. It means you have a security of 128 bits, the size of the key. In the public key business, it's much more complicated. And specifically in the case of lattice-based crypto, it's very unclear how you get from a specific set of parameters to a quantified security level. So quantifying the security level just means getting an order of magnitude of the least amount of operations needed to break the system. And that was the hardest problem researchers had to solve.
Are you seeing similar or different problems, Eli? Or you're seeing different methods of solution? Where you
for what? For constructing post-quantum secure things.
Yes.
Yeah, maybe I'll say a few words on proof systems, and in particular on Starks and on ZK Starks. So proof systems, they come from this world of computational complexity, and they basically do some things that are completely magical. I mean, but again, just like cryptography is doing some things that are completely magical, so also proof systems do something that is completely magical, which is suppose you, I mean, what they do is deliver computational integrity very cheaply. So what do I mean? Suppose you want to know whether someone ran a very long computation correctly and didn't make any errors, or is not cheating you with replying, with the end result. For instance, suppose someone claims to have processed 10,000 blocks of Bitcoin and gives you the state of the system afterwards, what's called the UTXO, and wants to convince you that those 10,000 blocks led to a situation where he owns all of the Bitcoin in the world. Okay, so how do you prevent someone from presenting to you something like that without lying? So the solution that Bitcoin has to this is, well, everyone in the network is basically going to check and inspect each and every transaction in each block, and we're just going to see for ourselves whether indeed the state of the system has been transitioned with integrity. So what proof systems allow you to do is something completely magical. They say, even without trusting anything about this party that is claiming to have processed the transactions, they could be Darth Vader and have all the power of the NSA and even more, and we have no trust assumptions about them. There is a mathematical method for us, for the public, to be sure that the new state has been computed with integrity, even when the party running the computation is extremely powerful, even more powerful than a quantum computer, and really is incentivized to misreport the output. And we can do this not just without following the whole computation, we can do it exponentially cheaper than it would take us to run the computation. In fact, we can do it in logarithmic time. So if there were 2 to the 50 transactions being processed, we can check it in logarithm of 2 to the 50, which is 50 steps or so, rather than 2 to the 50. And this is just completely mind-boggling and amazing. And it is so mind-boggling and amazing that the inventors and early pioneers of this field won a bunch of awards, starting from the Turing Award for Shafi Goldwasser and Silvio Micali, through the Gödel prizes, and the most recent, and Nevalina prizes. The most recent was the Abel Prize, given this year, partially also for contributions to this field, to Professor Avi Vigdelson, who was my PhD advisor and is also a scientific advisor to StarkWare. So all of this amazing concept of being able to verify very succinctly an immense amount of computation without trusting the party running that computation is a very powerful paradigm. And it was theoretical for 35 years or so. And in the research that a bunch of people, myself and a lot of collaborators over these 3.5 decades have done, it was to make this thing practical. And now, we have these systems basically running on blockchains, processing millions of transactions and convincing the world that they're okay. And one of the nice things is that these systems are so powerful that you need very little cryptography. In fact, the only cryptography that you need is a hash function. And hash functions happen to be post-quantum secure. So you can take all of the amazing benefits of proof systems, the privacy, zero knowledge, the computational integrity, the succinct verification, and have them be post-quantum secure pretty much for free. And that's so for instance, right now, the way payments are being paid in Bitcoin and other cryptocurrencies is by using digital signatures that rely on number theoretic assumptions. These assumptions would be broken if a quantum computer ever existed with a large number of qubits. But the good news is that you can take those, easily replace them with zero knowledge based on a ZK Stark. In fact, we even have open source code for it called Siggy. You can look it up. And now you'll get the same kind of digital signatures, post-quantum secure, but you'll get a lot more because zero knowledge proofs are much more powerful than just signatures. So
that's actually a wonderful summary, and it's taken away a considerable amount of the hype that seems to be generated out there at the moment. I hope that with the next 10 minutes, just to close off, that JP, start off with what you see as the remaining threats and possibilities, with optimism, both near term and long term, where you see there are further research priorities, and where you think investment priorities should be focused now.
Yeah, so there's a kind of theory of evolution of cryptography whereby you start with the fundamentals, the math, then the research papers, then the things that are not practical, then they move from theory to practice, and now they're moving faster and faster. So you first go from the theoretical security, from the security proofs, and then you need to scale it, you need to implement it efficiently, you need to document it in a clear way to prevent people from misusing it. And I think we are at this stage with zero knowledge proof and proof of knowledge in the context of blockchain applications. And as much as I'm skeptical about the value of certain blockchain projects, I think it's been a huge driver for cryptographic research in this kind of problem. And I usually don't like to use this word, but I think this category of techniques is to some extent disruptive in the sense that it enables new applications and to do certain things on chain that you could not do before, or at least do them on chain, so publicly, but by hiding the information you want to hide, so thereby enabling some privacy preserving applications, and also minimizing the storage on chain. So yeah, just to continue with the answer to this question, I think, so I've done a lot of security audits of blockchain crypto projects, and I've sometimes found beautiful works and protocols, ZK Snarks and ZK Starks, really secure on paper, but they were sometimes quite complex. And when something is complex, then you have a higher risk of errors. So the biggest risk from my perspective is bugs in the implementation. It can be software bugs. It can be also misimplementations of something specified. So you implement something a bit different. It can also be that the initial designers, they had maybe an incomplete specification, or they had a threat model, an attack model that was not adequate in practice. And the biggest problem is that, unlike a block cipher or simple hash function, which are fairly easy to review, to gain confidence in, the problem with ZK Snarks and Starks is they tend to be very complex. This step where you go from, let's say, business problem to an arithmetic circuit, it tends to be hard. And that's why researchers, I think from StarkWare and other places, they've worked to, on the one hand, make this simple with maybe simpler languages, and to automate it as much as possible to avoid mistakes. But maybe some of the scariest securities I've done in my life were about reviewing this kind of technology where at the end of the day was like, guys, I did not find critical bugs, but I'm not really sure of myself. I don't claim to have a full understanding of what you do. And maybe one example of this is the Zcash platform. They've done a lot of audits. They have very competent scientists. They have very competent implementers. But nonetheless, I think a very critical bug was found by the Zcash people, I think 1 or 2 years after the deployment, and they rapidly fixed it, and nobody died. But it really stresses that you really have to be an expert and have a 200% understanding to find the very subtle flaws in this kind of technology.
So, Eli, it's over to you to bring it home. Where do you see the near-term research priorities and investment priorities so that we keep ahead of the curve?
Yeah, okay, there's a large scientific effort spearheaded, or there's also this sort of challenge given by NIST for forming post-quantum cryptographic primitives, and that's one area. The area in which we hope to contribute to post-quantum security is through, and I want to refer to this point that Jean-Philippe was talking about, exactly making things safer to use for developers as they use things like ZK Starks. And I completely agree that any new technology, especially if it's very complicated, like things like Starks and Snarks, you're going to have all kinds of bugs that might be threatening. So the way we're approaching it is, what if you had, basically, if you moved as quickly as possible, or if you had as simple, a set of math principles or things to inspect, and having inspected them, you have at your disposal a general purpose CPU or programming language. So now you have a very limited challenge of checking that a small set of a very small system has been designed well, and of course it's challenging and so on. But once you've done that, now you're within the world of programming, which has a well-established set of tools for testing code and debugging and so on. And this is precisely what we did at StarkWare with this programming language and framework called Cairo. So we designed a system that has something like 50 polynomial constraints that define a CPU, and the CPU's general purpose. And we're even embarking on formally proving that these 50 constraints indeed implement the CPU functionality that you need. And once you've done that, now you sort of reduce the problem of security to this well-known earlier problem of writing sound code, which is, of course, all, complicated problems are always complicated, but at least you've reduced it to some well-established discipline of programming. And that's what we've already accomplished in StarkWare with Cairo, and it's now actually accessible to everyone through StarkNet.
Eli and JP, thank you. We have an enormous debt of gratitude for your time and insights. And if anyone should want to get in contact with you, can do that directly. In the bio, there's a reference to your contact details. So once again, thank you from all of us at CogX.
Thank you so much.
Thank you for having us.
Yeah, thank you so much, Eli, JP, and Michael, for such an illuminating panel. It was really awesome to dive into a more technical discussion. So we now have an afternoon break until 5 p.m. BST, where we'll be back for gaming, shifting from the play-to-win to play-to-earn game models, moderated by Fabric Ventures partner Max Mash. You are watching the Open Web Forum, curated by Fabric Ventures. Be sure to check out our Twitter @Fabric_VC, and see you all in 20 minutes.